9C heat. 9.1 The nature of heat. Remember the last time you opened a car door on a broiling summer afternoon and were met by a blast of hot air? After gingerly seating yourself on the hot seat, you quickly became aware of its ability to store energy. The longer you sat there, the more you felt the sun pouring additional energy into you and the car. All these sensations are evidence of heat, the flow of thermal energy from one place to another. In everyday situations, the word heat is often loosely used for both thermal energy and temperature. You have probably heard it said that a boiling pot has a lot of heat, thermal energy, or the oven is set to high heat, temperature. Neither of these statements is correct from a scientific point of view. The amount of thermal energy in an object is a property of the object. It has thermal energy. In science and in this textbook, heat is used as a noun only to identity a quantity of thermal energy that moves between systems. Heat is not something that system has. The best way to use heat is as a verb to describe processes in which thermal energy is added or gained. A stove heats a pot of water. The opposite process is to cool, to remove or lose thermal energy. Heating and cooling occur through one of three processes: conduction, convection, and radiation. Heat transfer, conduction. When two objects of different temperatures touch, thermal energy moves from the hotter to the cooler object. This process is called conduction. How does conduction transfer thermal energy? When a warmer object contacts cooler one, its faster-moving particles collide with the cooler object's particles, transferring kinetic energy. The object with more thermal energy will cool, and the second object will warm until both are at the same temperature. At this point, the average kinetic energies of all their particles are the same. Their temperatures are the same. These objects have attained thermal equilibrium. When one object is a continuous source of thermal energy, such as a stove burner, another object in contact with it continues to gain thermal energy until reaching thermal equilibrium with the first. Ideally, the temperature at which thermal equilibrium occurs would be equal to the source's higher temperature, but this does not normally happen. Thermal energy is continuously lost by the second object to its surroundings. Its surface remains cooler than the temperature of the hotter source, so thermal energy continues to flow. Conduction is the chief process by which thermal energy moves through solids. Because the atoms of solids are tightly bound to each other, one strongly vibrating atom collides with adjacent atoms, causing them to vibrate more. Thermal energy thus moves quickly throughout the solid material. All materials can conduct thermal energy, though some do so better than others. Diamond is the best natural conductor of thermal energy. Metals, because of the special way their atoms bond together, are generally excellent thermal conductors. Silver is the best metal for conducting thermal energy, but it is also relatively expensive. In most situations, less expensive conductors, such as copper and aluminum, are more practical. Substances that are good thermal conductors are usually good conductors of electricity also. Having an efficient thermal conductor is important when a large amount of thermal energy must be transferred. The heat exchangers and radiators in heating and cooling systems often have fins and coils made of thermally conductive metals. Convection. That blast of hot air that greets you when you open a car door on a sunny summer day illustrates another method of thermal energy, flow convection. In convection, thermal energy is carried from one location to another by a fluid. Convection involves the movement of randomly vibrating atoms and molecules over distances that are large in comparison to the size of an atom. For this reason, convection does not occur in truly solid materials, but it is the most important way that thermal energy is transferred within fluids. Natural convection occurs under the influence of gravity. Warm fluids rise and cold fluids sink due to differences in density. A heated fluid's particles move faster. The fluid occupies a greater volume of space, as the more frequent collisions of its particles force them farther apart. Since the same number of particles occupies a larger volume, the fluid's density is lower and it becomes buoyant relative to the cooler surrounding fluid. See Chapter 8. The denser fluid flows in under the less dense fluid, forcing it upward. This process continues as long as there is a thermal energy source for the fluid. After the warmer fluid rises, it immediately begins to transfer thermal energy through conduction to the cooler fluid around it. This cools the rising fluid. Eventually, its density is greater than the fluid rising beneath it, and it flows to the side of the rising column and sinks down toward the heat source to begin the cycle over again. The fluid's cyclic path is called a convection current. Hot water radiators and electric baseboard heaters heat rooms by setting up convection currents. The warm air in the vicinity of the radiator rises by convection and flows toward the ceiling in the middle of the room, cooling as it goes. It then sinks to the floor and flows back toward the radiator to replace the less dense, warmer air that continues to rise. Forced convection is often used by engineers to increase the capacity and improve the efficiency of convection heating and cooling systems. Fans move air in ventilation systems and in convection ovens. Pumps move liquids through heating and cooling systems. Atmospheric convection is responsible for many kinds of winds near the Earth's surface and for large-scale atmospheric circulation. Local atmospheric convection currents include sea and land convection current breezes, as well as mountain and valley breezes. See Figure 9-29. Immense convection currents affect global weather by exchanging warm tropical air from near the equator for the cooler air at higher latitudes and the frigid air at the poles. Global convection currents keep the Earth's surface temperature within habitable limits. Without them, the equatorial regions would bake, while the higher latitudes would be locked in ice. Radiation. How do the immense quantities of vital thermal energy move from the Sun through 150 million kilometers of empty space to the Earth? The density of the particles that do exist between the Earth and the Sun is too low to transfer thermal energy by conduction or convection. Thermal energy moves most efficiently through a vacuum as radiant energy. It is converted to electromagnetic energy at its source, and then converted back to thermal energy at its destination. As electrons move about the nucleus of a vibrating atom, the atom exchanges energy with its surroundings in the form of electromagnetic energy. All atoms emit this energy, particularly as infrared energy. The higher the temperature of the substance, the more electromagnetic energy is emitted. Electromagnetic energy moves in space through the process of radiation. See Chapter 6 and 14. The hot plasma of the Sun's surface contains great quantities of thermal energy. The highly agitated plasma ions emit intense radiant energy of all kinds into space. This electromagnetic energy races outward in all directions at the speed of light. A tiny fraction of this energy falls on the Earth. Atoms in the atmosphere and on the Earth's surface absorb the Sun's radiant energy. They vibrate faster, and their average kinetic energy increases, causing the Earth's temperature to rise. Because thermal energy can be transferred by radiant energy, many people consider them to be the same thing. However, radiant energy is distinct from thermal energy in that it does not use matter to move between systems. Radiant energy can transfer thermal energy between two objects that are not in contact. If they are not in thermal equilibrium, the infrared emissions of the warmer object will be greater than those of the cooler. The cooler object will absorb the excess infrared and grow warmer. This principle is the basis for medical heat lamps used to keep injured limbs warm, allowing healing to occur. Food displays in restaurants use infrared lamps to keep food hot. You may have noticed that on a sunny day you feel warmer wearing a dark-colored shirt than you do wearing light-colored one. The amount of radiant energy that is absorbed depends on certain properties of the material, one of which is color. For instance, dark-colored materials readily absorb radiant energy, while light-colored materials reflect most of it. Chapter 15 discusses how color affects absorbed and reflected light. 9.12 Insulation and Thermal Resistance. Some materials, rather than being good conductors, seem to hold thermal energy at bay. Materials that resist the flow of thermal energy are thermal insulators. The atoms of good conductors are bonded closely together, and they have many loose electrons that can easily move among the atoms. When the atoms vibrate, motion is quickly transmitted throughout the material by moving electrons. Just as the properties of conductors arise from the arrangement and bonding of their atoms, so do those of insulators. The atoms of some insulators are bonded together in open, sponge-like structures, while other insulators have their atoms bonded close together with the electrons held tightly to the atoms. When thermal energy is transmitted to the surface of the material, few atoms or electrons are affected by the vibrations, and it takes a long time for thermal energy to move through the material. Insulators may be natural or man-made. The best artificial insulators are aerogels. Read the facet on the following page to learn about these fascinating materials. Gases can be good insulators because their particles are so far apart that they do not efficiently transfer thermal energy from particle to particle. Insulated windows consist of two panes of glass that confine a thin layer of dry gas between them. The gap must be less than a centimeter wide to keep a convection current from occurring, and the gas must be a relatively poor conductor. Gases that are confined so that they cannot produce convection currents prevent almost all thermal energy flow by conduction through the glass. The trapped air inside the cells of polystyrene foam or among the feathers in a down jacket achieves the same effect. The insulating ability of a material is increased by the air gaps it contains. The best insulator of all is a vacuum, because there are no particles present. The only way thermal energy can move across a vacuum is through radiation, which is not as efficient as conduction. Vacuum insulation is commonly used in insulated containers to keep food warm or to maintain extremely low temperatures in bottled liquefied gases. 9.13 Measuring heat in thermal energy changes. Heat capacity. Good thermal conductors, such as metals, need to absorb only a small amount of thermal energy to noticeably raise their temperature. However, insulators, such as fiberglass, must absorb a lot of thermal energy before they show a similar temperature change. Every object has a particular relationship between the amount of thermal energy absorbed and the temperature change experienced. This property is its heat capacity C. Heat capacity is the thermal energy in joules that an object must gain or lose to cause a temperature change of 1 degree Celsius. The unit for heat capacity is joules per degree Celsius, or joules per Kelvin. This value depends on the amount and kinds of materials in an object. Heat capacities for objects that are made of more than one kind of material must be determined experimentally. Because thermal energy is being transferred, the change in thermal energy that results in a change of temperature or state is called heat, Q. The heat capacity of an object is computed by dividing the heat gained or lost by the change in temperature C equals Q over delta T, where C is heat capacity, Q is the thermal energy transferred to or from the object in joules, and delta T is the associated change in temperature in degrees Celsius. You can see from the formula that the larger the heat that causes a given change in temperature, the larger the heat capacity of the object. Specific heat capacity. Good thermal conductors have low heat capacities, and insulators have large heat capacities. But mass as well as thermal conductivity determines an object's heat capacity. Comparing heat capacities of different materials is not very meaningful unless you compare similar masses of the materials. A much more useful property for identifying materials is specific heat capacity, or just specific heat, CSP. Specific heat is the heat capacity per gram of material, the amount of thermal energy that must be gained or lost to change the temperature of 1 gram of the substance 1 degree Celsius. The SI unit for specific heat is joules per gram. C. Specific heats of metals are much lower than those of other materials. The specific heat of the gaseous phase of a substance is much higher than for the same material in its liquid or solid state. If an object has uniform composition, such as a solid brass cylinder or a liter of alcohol, you can determine its specific heat by dividing the heat, thermal energy exchanged with its surroundings, by the object's mass and its temperature change. CSP equals Q over m times delta T. An object's specific heat can be determined with a calorimeter, a device that measures transfers of thermal energy between objects contained in an insulated chamber. One common activity of science is to measure physical properties, such as specific heat. For newly developed materials, this helps engineers know where the material could best be used. Once researchers know a material's specific heat, they can use it to compute temperature changes and thermal energy gain or loss for an object made of that material. Such calculations are important in designing systems with heat exchangers. Specific heat capacity is essential for optimizing the operation of solar thermal power facility collectors and steam plants, which are used to convert solar energy to electricity. For these purposes, the heat equation used is just the rearranged specific heat formula, Q equals m times C SP times delta T. Of all familiar substances, water is unusual because it has a relatively high specific heat compared to other liquids and chemically similar compounds. Water's specific heat is approximately 4.18 joules per gram Celsius. Compare water to the other familiar substances in Table 9.1. Water's large heat capacity allows perspiration to be an effective cooling mechanism for our bodies. It also allows large bodies of water to modify weather over adjacent continents. For example, the British Isles have a more moderate climate than other land masses at the same latitude because of the warming effect of the Gulf Stream in the Atlantic Ocean. 9.14. Heat and phase changes. When thermal energy is added to or taken from a material, the material's temperature usually changes because the average kinetic energy of its atoms and molecules changes. But sometimes the temperature doesn't change. For example, if you add many ice cubes to a glass of water at room temperature, the water quickly cools to near freezing. You slowly stir the water-ice mixture and monitor the temperature. The glass is uninsulated, so thermal energy from the room enters the water through the glass. You notice that the temperature of the mixture hovers near 0 degrees Celsius. The only noticeable change is the melting of the ice cubes. In ice, bonds between the molecules produce a potential energy that holds the molecules together. Work is required to pull the molecules apart, just as it takes work to pull apart attracting magnets. Thermal energy does this work, as it flows from the room through the glass and water. The liquid water does not warm up while the ice is melting, because the thermal energy is used to break the bonds between the molecules of ice. It requires more than 333 joules to melt 1 gram office to 1 gram of water at 0 degrees Celsius. As 333 joules per gram is taken from the surroundings to melt ice, the same amount of energy per gram is transferred to the surroundings when water freezes. The amount of thermal energy exchanged per gram of material during melting or freezing is the material's latent heat of fusion, L. Once all the ice is melted, the liquid water will continue to warm at a rate determined by its specific heat, about 4.18 joules per gram per degree Celsius. Similarly, when a liquid begins to vaporize at its boiling point, the temperatures of the liquid and gas do not rise until the liquid is completely vaporized. In this phase change, thermal energy is used to boost individual molecules into the gaseous phase, rather than to increase the average kinetic energy of the liquid phase. Every gram of liquid water requires 2,256 joules of thermal energy to vaporize at 100 degrees Celsius. This is called the latent heat of vaporization, L. When condensing, steam must lose the same amount of thermal energy to its surroundings. Every substance that can exist in more than one phase has its own latent heats of fusion and vaporization, which are characteristic for that material. Water has unusually large latent heats, especially for vaporization. This is why it is the preferred fluid for transferring thermal energy in powerful engines, such as steam turbines. Once water is turned into steam, it can give up a large amount of energy per gram for work as it condenses back into a liquid. In summary, every substance has a distinctive specific heat, one each for its solid, liquid, and gaseous states, if applicable. In addition, each has a characteristic latent heat of fusion, and of vaporization if it can exist in liquid or gaseous states.